In this video, we're going to talk about how to find a confidence interval for a population proportion. The previous two videos were about finding confidence intervals for means in various situations, and now we're going to switch the parameter to a proportion or the percentage of the population that has a particular quality. We're not nearly as familiar with the idea of estimating a proportion as we are with estimating a mean, so we're going to need a little bit of backstory here. The point estimate for a population proportion is the sample proportion. So if you need to know the proportion of a population that has a particular property, but you don't have access to the entire population, you do the same thing you would do for a mean. You would gather a sample and then find the proportion of the sample that has that property. We use that sample proportion as an estimate for the population proportion. Here's a little bit of notation. The notation for a population proportion is lowercase p, which is the same as the notation for the probability of success in a binomial experiment. And the notation for a sample proportion is this p with a little 2/3 of a triangle on top. And we call this a hat. And so the way we read this is we say p hat. I put that hyphen in there so it doesn't look like I'm coming straight out of the 90s and saying fat. That's p hat. It's not cool, it's p hat. So p hat is a point estimate for p. The way we calculate p hat is pretty straightforward, but I'm going to write the formula out anyway. To calculate p hat, you take the number of observed successes in your sample and you divide by the size of the sample. Remember that we called the number of successes x in a binomial experiment, so we're going to continue with that notation here. And our sample size has been called n throughout the course. This is the same notation that our calculator will use when we learn the calculator function for this section. We've talked about estimating means before, but we've never done an example of estimating a proportion. So let's do an example here. A random sample of 150 American adults reveals that 54 registered for an online dating site or app. Use this data to find a point estimate for the proportion of all American adults who have created an online dating account. All right, we can't actually track down every single American and ask them whether or not they've ever registered for online dating, but we do have the sample data to work with, and we can use this to generate a point estimate. The point estimate is denoted by p hat. So you draw this little 2/3 of a triangle, you give p a little hat. And we calculate p hat by taking the number of observed successes and dividing by the sample size. Now the sample size is 150. A success would be an American adult who has created an online dating account. And we're told that the sample has 54 such people in it, so the number of observed successes is 54. You could leave that as a fraction. This fraction happens to reduce. A lot of times we turn these proportions into decimals or percents. 54 over 150 comes out to 0.36 or 36%. And all of those are acceptable ways to represent the sample proportion. I actually choose my answer based on the way the problem is worded. This problem used the word proportion, and so I would probably use the decimal. If instead it had asked for a point estimate for the percentage of all Americans who have created an online dating account, then I would have used the percent. Now, we have the same issue with point estimates here that we did with means. When you calculate a point estimate, you really have no gauge of whether or not that's a reasonable estimate. But a more concrete way to do that would be to construct a confidence interval. Now, here we're looking at the distribution of the sample proportions, not the sample means, and so we're going to need a crash course in that distribution. We won't learn it as in depth as we did with means, but here's a quick slide to describe what's going on. The distribution of the p hats is technically binomial because it varies based on the number of successes, and the number of successes would be a binomial variable. But it turns out that if you know that n times p hat is greater than or equal to 5, and n times the quantity 1 minus p hat is greater than or equal to 5, then the normal distribution with mean p and this goofy standard deviation is a good approximation for the distribution of the p hats. So we can use a normal distribution to approximate the pattern of variability of the p hats as long as both of these conditions are met. And we've written these in kind of a nerdy way using inequality notation, but there's an easier way to say this. Remember that p hat is x over n. So n times p hat is n times x over n, and those n's would cancel and we just get x. So another way to say this is that x is greater than or equal to 5, and x is the number of observed successes, so you need at least 5 observed successes. And I'm not going to drag you through the same calculations here. You can verify this on your own. N times 1 minus p hat would be the number of observed failures, so you need at least 5 failures as well. As long as your sample has at least 5 successes and at least 5 failures, so 5 outcomes in each of the 2 categories, then you can use a normal distribution in order to approximate the distribution of the p hats. So that distribution would look like this. Notice that I'm using mu sub p hat, not mu sub x bar, because this is the distribution of the p hats. And the thing we're trying to estimate, we don't know what p is, that's what we're trying to estimate. But the thing we're trying to estimate is dead smack in the middle of the distribution, just like it is for the means. And we have a formula for the standard deviation, although we can't actually do this calculation because we don't know what p is. So we would estimate it with p hat. So this now becomes an estimate. But we use that as our standard error. Because we're using a normal distribution, we would need to know how far we have to go in that normal distribution in order to get a desired confidence level, and this would work just like z-interval does. So we would know, for instance, if you want 95% confidence, you have to go 2 standard deviations away from the mean. And so to construct a confidence interval with 95% confidence, we would hop 2 standard errors away from our p hat. It works the same way. I'm not going to drag you through all of that again. Here are the steps. If you're constructing a confidence interval for a population proportion, you gather a simple random sample of size n, you count the number of observed successes, and you have to verify that there are at least 5 successes and at least 5 failures in the sample. If there aren't, then that normal distribution that we were using isn't necessarily valid. You compute p hat by taking the number of observed successes and dividing by the sample size. P hat is just x over n. You choose a confidence level. 90%, 95%, 99% are the most common. And then you calculate the bounds of the interval by adding or subtracting the appropriate multiple of the approximation to the standard error to and from p hat, creating the bounds of the interval. This distribution isn't something that we studied very well, so it wouldn't be fair of me to ask you to ever do this by hand. Thankfully, we've got a calculator function to do this for us. To find a confidence interval for a population proportion, which we denote by p, we use a calculator function called 1PropZInt. 1prop stands for a single proportion, one proportion. The z is there to remind us that we're using the normal distribution as an approximation to the distribution for the p hats. And the int stands for interval. So 1PropZInt. Unlike the calculator functions for means, this calculator function only requires 3 inputs: x, the number of observed successes, and the sample size, and the confidence level. The calculator takes x and divides it by n to get p hat. It uses that p hat as part of the estimate for the standard error. It then takes your confidence level and converts that to the number of standard errors we would have to hop in order to enclose that percentage of the p hats in our estimate. And then it adds and subtracts that number of standard errors to and from the sample proportion in order to create the interval. Let's look at an example, and as we do this, we want to point out not only how we use this calculator function, but before that, we need to really talk about how we know this calculator function is the appropriate choice. It says a random sample of 150 American adults reveals that 54 registered for an online dating site or app. Use this data to construct a 95% confidence interval for the proportion of all American adults who have created an online dating account. So in the earlier example, we were asked to find a point estimate. Now we're finding a confidence interval. But that on its own doesn't tell us that this is a 1PropZInt problem. We found confidence intervals before, and we used z-interval or t-interval, but those were confidence intervals for means. This is a confidence interval for a proportion, and that's what tells us that this is a 1PropZInt problem. 1PropZInt is the calculator function that we use to find confidence intervals for proportions or percentages. Recall that it's going to ask us for 3 inputs: the number of observed successes, which we call x, the sample size, which we call n, and the confidence level. We already identified these when we did this problem before. There were 54 observed successes. There were 150 in the sample. Notice that we have at least 5 successes, and we have at least 5 failures. You can tell we have at least 5 failures because 150 minus 54 is greater than or equal to 5. So we've satisfied that assumption. We're good there. And then the confidence level that was given to us is 95%, which is easily the most commonly used confidence level. So let's demonstrate how to use the 1PropZInt calculator function. You're going to push stat, scroll to tests, And 1PropZInt is choice A. It might be faster to scroll up instead of scrolling down, but I already started. So here's choice A. Remember that if you don't want to scroll to choice A, you can push alpha and the key directly below it. You'll see a green A above that key. So you push your green key and then the key directly below it to just select option A. I've already scrolled all the way down to it, so I'm just going to hit enter. And you see it prompts you for X, N, and a confidence level. It uses the same notation that we mentioned before. The number of observed successes was 54. The sample size is 150. And you can see that from a previous example, I already have the 95% in there. You just type 0.95. Enter. And now the calculator is going to first come up with that point estimate that we came up with, which is 0.36. It's then going to use that p-hat to estimate the standard error using that formula we saw on a previous slide. It's then going to say, okay, to get 95% confidence, we're going to have to hop almost 2 standard deviations away from the mean, and it's going to add and subtract that multiple of standard errors to and from our p-hat in order to come up with the interval. To us, it looks like magic because it happens almost instantaneously when you hit enter. And we get our estimate. Notice that directly below our confidence interval, you see this p with the 3 pixels on it. That's the calculator's attempt to draw a p-hat, and it's the same value we came up with, 0.36. That's the center of the interval. If you were to add these two proportions together and divide by 2, you get 0.36 because it's in the middle. It's the center. So let's copy down this interval. So now we get to the point where we have to write the interpretation. And while the theme of the interpretation is the same, the wording is going to be a little bit different than the ones that we wrote before because this isn't about a mean. We're still going to start by bragging about how sure we are that we're right. We are 95% confident. And now your intellectual muscle memory kicks in and you want to write that the mean, but this isn't for a mean. Let's go back and look at the problem. This is a confidence interval for the proportion of all American adults who have created an online dating account. We are 95% confident that the proportion, not the mean, of all Americans, and you can't stop here with the population because you have to explain which segment of the population you consider to be a success. What are we talking about here? The proportion of all Americans who like ketchup on their eggs? The proportion of all Americans with back hair? No, we're talking about the proportion of all Americans who have created an online dating account. And what do we think about that proportion? Well, we think it's between those two bounds. Because we used the word proportion here, I would leave these as decimals. However, it is okay to change those to percentages. But if we were going to change those to percentages, then I would encourage you to also change this word to percentage. And if I were writing this for publication, I would almost certainly do that. But I've been pushing on you guys to just copy the wording in the problem, and so I'm going to continue to do that. Since the problem used the word proportion, I'm going to use the word proportion, and therefore I'm just going to keep these as decimals. It would not be wrong to change these into percentages. I just think that that might lead to the potential for misunderstanding that these were less than 1%, when in fact this is somewhere between 28% and 44% if we round. Now you can see that's a fairly wide interval. It's over 15 percentage points wide. So there's a lot of error here, and that's because of the size of our sample. If we wanted to reduce the amount of error in our measurement, then we would increase the sample size. Or I guess we could decrease the confidence level and sacrifice some accuracy for the precision. Just like for means, there's actually a formula that will tell you what sample size you need to reduce your error to a certain amount. You've almost certainly seen this taken into account when you've seen an online poll or something on television and they say the margin of error is plus or minus 3%. They've selected a sample size that reduces the error to that amount. Our margin of error is over 7.5%, and that's primarily due to our sample size. Before we move on to the next example, I just want to show you that the theme of our interpretation is still basically the same. We want to say how confident we are. We mention the parameter. It's just the parameter is not a mean anymore. It's a proportion. We mention the population, but now we have this extra piece where we have to talk about the segment of the population that we consider to be a success, and then we mention the interval estimate that we came up with. Very similar with that one extra part where we have to talk about what we consider to be a success. Let's try another one. A random sample of 326 people were asked if they walk when using an escalator. There were 171 people in the sample who say they usually do walk on escalators, and I love these people because the escalator isn't a ride, so if you have the ability, you should be walking up or down it not treating it like you're at a carnival. Anyway, let's find a 99% confidence interval for the proportion of all people who usually walk on escalators. Okay, what are we being asked to find? A confidence interval. Well, that doesn't help. Almost everything we've talked about in this chapter has been about confidence intervals. That could be any of our three calculator functions, but keep reading. It's a confidence interval for a proportion, not a mean. And that makes this a 1PropZInt problem. 1PropZInt is going to ask us to identify the number of observed successes, which the calculator calls x, the number of trials or sample size, which we've called n all semester, and the confidence level. A success is somebody who walks when they're on an escalator, not just because of my bike. That's the proportion we're being asked to find, the proportion of all people who usually walk on escalators. There were 171 people in this sample who walk on the escalator. Usually, anyway. The sample size is 326, and the confidence level that was selected for us was 99%. Let's throw this into the calculator to get our estimate. Stat. Scroll to tests. You want choice A, so alpha and the math key on my calculator will select choice A. We had 171 successes. Our sample size is 326, so you could think of that as the number of trials in our experiment. And we've got a confidence level of 99%, so 0.99. The calculator is going to take 171 divided by 326 to get a point estimate. It's going to use that point estimate to approximate the standard error. It's then going to figure out how many hops you have to go in a normal distribution in order to get 99% of the area. We're assuming that the normal distribution is going to be a good estimate because we've got at least 5 successes and at least 5 failures. The at least 5 failures comes from subtracting these two numbers, not just based on the sample size. You subtract. And then it adds and subtracts to get the interval. Again, we just get to hocus pocus this. And we get an interval that ranges from 0.45329 to 0.59578. And now we write our interpretation. We are 99% confident that the, stop your hand from writing mean. This wasn't for a mean. We're estimating the proportion. Proportion of what population? All people. Proportion of all people who have what property? Who usually walk on escalators. That part's important. Don't forget to point out what segment of the population is considered to be a success. And what are we so sure about? That the proportion of all people who usually walk on escalators is between those two bounds. You might choose to write them as percentages because that feels a little more natural, somewhere between 45.329% and 59.578%. I would encourage you that if you do that, you change the word proportion to percentage. I don't know if it's fair to say that that should be required, but it avoids ambiguity that people might think that you're talking about 0.45% here instead of 45%, which is what it really means. So we're very sure that somewhere between 45 and 60% of all people walk on escalators most of the time. Bless them all. Here's another example. A random sample of 203 cell phone users is collected. In this sample, there were 45 people who had dropped their phone in a toilet. This sample data did not reveal how many of them retrieved their phone. If it were a public toilet, or even worse, a porta potty, mine might have to stay. I don't have a smartphone, so I'd be willing to sacrifice mine. But I guess if you drop a $1,000 phone into the commode, maybe you have to go get it. Anyway, use this information to construct a 90% confidence interval for the percentage of all cell phone users who have dropped their phone in a toilet. This is another confidence interval, and it's not for a mean. It's a confidence interval for a percentage. Now, I know that's worded differently because we said that 1PropZInt is for proportions. But remember that you can convert easily between percentages and proportions by just swinging the decimal point and either adding or subtracting a percent symbol. So this is the same kind of question. This is a 1PropZInt question. It's definitely not for a mean, so Z interval and T interval are out. By process of elimination, it's got to be 1PropZInt. But also notice that it's got the same kind of information that we usually get for proportions. We've got a number of observed successes and a sample size, which is exactly what we need. We're considering a success to be somebody who dropped their phone in a toilet, not because it's hilarious, but because that's what we're being asked about here. There were 45 people who dropped their phone in a toilet. The sample size is 203, and we want 90% confidence. Press Stat, scroll to Tests, choice A. We had 45 people in the sample who dropped their phone in the toilet. There were 203 people total. We want 90% confidence, so 0.9. Calculate. This one ranges from 0.17372 to 0.26963. So a margin of error just under 5%, right? That total range is just under 10%. And so our margin of error is around 5%. If you thought that was too big, you just need a bigger sample size. You need to gather more data. Increasing your sample size will decrease your margin of error, all other things equal. I know we've only done 2 of these so far, but try pausing the video and see if you can write this interpretation. We start by saying how sure we are that we're right. We are 90% confident. A lower confidence level than the previous 2 examples, which is one of the reasons why our interval is tighter than usual. We again sacrifice some accuracy for precision. But 90% confidence is still pretty sure that stop yourself. It's okay to write proportion. I'm worried that you wrote mean. It's not a mean here, but I wouldn't write proportion either, because remember how the problem was worded. It said the percentage of all cell phone users who have dropped their phone in a toilet, and so I would say the same thing. It's okay to write proportion, but since the word problem said percentage, I would say percentage. And we're 90% sure that this percentage is between these 2 bounds, but because we use the word percentage, I would convert these to percents. 17.372% and 26.963%. Again, I think that would avoid any confusion that somebody might have that maybe those decimals were supposed to be less than 1%. That's not what we mean here. So to be clear, I write these as percents if I use the word percentage. So 17% is more than a sixth, so we have strong evidence to suggest that more than a sixth of all cell phone users have dropped their phone in a toilet. Maybe that's horrifying, maybe it's funny if it's never happened to you, but that's what we can determine using this data. Okay, one more example, and this one's more along the lines of how this gets used in the real world. There are surveys about the percentage of people who use online dating apps. That's good for marketing and so on. The other 2 about walking on escalators and dropping your phone into a toilet are more trivia than anything else. But this last example is how somebody would use this in the real world for quality assurance. A large shipment of electronic parts is sampled to look for defects. In a sample of 1,016 parts, 22 are found to be defective. Construct a 99% confidence interval for the proportion of all parts in the shipment which are defective. You've got this shipment of millions and millions of parts, and you want to gauge what percentage of them are defective. You don't have the time to test them all, so you randomly sample 1,016 of them and you test those. Much more manageable. They find that 22 of those are defective, and we're going to use that to estimate the proportion of all of them that are defective. This is a confidence interval for a proportion, so this is a 1PropZInt problem. Pretty straightforward, I think. There were 22 successes. The sample size is 1,016. Again, you can think of that as the number of trials, like a binomial experiment. And the confidence level we selected here is 99%. They apparently want a high level of accuracy, and they've compared that with a high sample size. So the large confidence level wants to make the interval wider, but the enormous sample size will help reduce that. We've got this balance. We've got 22 successes, which is bigger than 5. We've got a ton of failures. Most of the parts work. That's good. We've got at least 5 successes, so the normal approximation is appropriate. We can use 1PropZInt. Stat, scroll to test, choice A. 22 defective parts out of 1,016 parts in the sample. We want 99% confidence, so 0.99. Calculate. And you can see we've got a pretty small interval here. The lower bound is around 1%, the upper bound is around 3.3%. So we've got a margin of error down to just over 1 percentage point. Our point estimate is around 2% with about a 1% margin of error, a little more than 1% margin of error. So we say we are 99% confident that the proportion of all parts in the shipment which are defective is between 0.00989 and 0.03342. And I haven't mentioned this in any of the examples prior to this, but when you're talking about proportions, proportions are unitless. So don't write a unit on the end of this. I wasn't forgetting to do that in the previous examples. It's incorrect to put units on the end. This isn't a number of parts. This is a proportion of parts. So you don't put any units like you would for means. So again, looking at our calculator output, the company could confidently state that around 2.2% of the parts are defective with about a 1% margin of error. They're 99% sure that they're within about a 1% margin of error. It's a little more than that, but around a 1% margin of error from that 2.2%. They could also confidently state that the percentage of all parts in the shipment that are defective is less than 4% because 4% doesn't fall on the interval. It's above the upper bound. Those are the kinds of extra things you could do with this. Our focus is going to be on writing the sentences, and that way other people could make those determinations. Most people find these problems to be easier than the previous two. Maybe that's because you've already got a little bit of experience with confidence intervals by the time you get here. I also think some of that has to do with the fact that there's no deciding between two calculator functions, and it's pretty easy to pick out what information you need. But if there's something in this video lecture that you didn't quite understand or you want more explanation on, don't be afraid to get a hold of me.